Hello and welcome to this video on how to run an exploratory factor analysis in SPSS. My name is Geiser, I'm an instructor with QuantFish. As you can see, I already have an SPSS data file open here on my screen, and I want to show you now where you find the options in SPSS for running an exploratory factor analysis. This data set here contains 7 variables. The first 4 are from a math scale with different subtests, and then the last 3 variables are from a cognitive abilities test. And so one question that I could have here is how many factors are needed to account for the correlations of these 7 variables, these test score variables. The variables are continuous or interval scale, and so therefore I can use a regular factor analysis based on the correlation matrix of the Pearson correlations of those variables. So let's get started and let's figure out where we find the options for exploratory factor analysis in SPSS. So for that we have to go to Analyze, and then you don't find factor analysis here, so it's kind of tricky to find because it is hidden under dimension reduction. So factor analysis is a method for dimension reduction, so figuring out how many factors we need to account for the correlations of a larger number of variables. So we simplify or we reduce the number of dimensions from 7 to hopefully fewer factors. So let's click on that. And then you can see, as usual in SPSS, you have your variable list on the left-hand side, and from that list you can select variables for the analysis. In this case, I'm going to select all 7 variables. I'm going to click them over into this field variables here. And then next we can get descriptive statistics under descriptive, so we can look at univariate descriptive statistics, and then also we can look at the correlation matrix of our variables, which is a good idea to always take a look at those as well. Then I'm going to click on continue, and next we're going to go to extraction. Under extraction, we can first of all select the type of factor analysis that we want to run here. And what is interesting in SPSS is that the default method is actually not factor analysis. So principal components is what SPSS would use by default, and principal component analysis is actually not factor analysis. It is a related technique that often leads to similar results, but the goals of principal component and factor analysis are quite different conceptually and theoretically. And so I'm not going to go into the details here, but most people would say, well, principal component analysis is not factor analysis. So if your goal is to do factor analysis, you have to pick one of the other methods here. And so what is one method that can be used for continuous variables and is useful because it provides model fit statistics is maximum likelihood estimation. So we can run a maximum likelihood factor analysis for our continuous variables here. And that way we will also get a chi-square test of model fit that will hopefully help us determine how many factors we need to extract here, because it provides a test of model fit for different numbers of factors. Under this option here, we can also obtain a scree plot. A scree plot is useful also for determining the number of factors. It allows us to plot the eigenvalues so that we can see how many eigenvalues in our data set are important or represent important factors. So we're going to take a look at this, and then you can see that under extract you can select the method based on which you want to extract or retain factors. And the default in SPSS is that all factors with an eigenvalue greater than 1 will be retained. So that is called the Geiser criterion, eigenvalues greater than 1, which is actually not a good criterion for selecting the number of factors. It usually does not result in the correct number of factors, but we'll go with that for now because we haven't seen the scree plot yet. We haven't seen the chi-square test of model fit yet. So we're going to just go with that for now and then decide if we need more or fewer factors. Then SPSS will choose based on this Geiser criterion of retaining factors with eigenvalues greater than 1. You can also fix the number of, you can select the number of factors yourself. So you can choose the second option and say, I want a specific number of factors that I think is best. And so we might do that later if we determine that the eigenvalue method does not result in a proper number of factors. So let's go ahead and click continue. And then next we're going to go to rotation. And rotation allows you to select either an orthogonal rotation method or an oblique rotation method. So you can rotate the factors such that they either will remain uncorrelated or orthogonal, or that they will be allowed to correlate. That's called an oblique rotation. And typically we have to do a rotation because an unrotated factor solution is typically not interpretable. Now, right now, we're not going to mess with that yet because we don't even know whether we need more than one factor. And if we only need one factor, then we may not, or then we wouldn't need to rotate the factor if there's just a single factor. So we're going to keep this as is. We're going to click on continue. And then next I'm going to show you the scores option here. So under scores, you can save factor scores as variables. So once you have a factor solution, then you can estimate the scores of the individuals on those factors, and they can be saved to the data set as separate variables. That can be useful if you want to summarize your data and use those scores for certain other purposes. So that would be kind of like a composite score or summary score that is based on factor analysis. Once again, we're not going to do that right now because we still don't know how many factors we actually need for these data. So I'm going to go and leave this as is for now and go to continue. And then under options, we can request that the factor loadings be sorted by size, which is useful to see more clearly which variables have high loadings versus small loadings. And then also we have the option of suppressing small loadings. For example, all loadings that are smaller than 0.1 could be suppressed to make the loading matrix easier to process, but I actually prefer to see all loadings, and so I don't use this option very much of suppressing small coefficients, but I do like the option of sorting them by size. You can also decide on the missing data method used. The default is listwise deletion of missing values. You can use pairwise deletion, or you could do mean replacement. Now, honestly, all three methods are bad, and that's actually one reason why I personally don't use SPSS for factor analysis very much, because when I have missing data, listwise deletion, pairwise deletion, or mean replacement are all bad methods for dealing with missing data. It would be better to use something like full information maximum likelihood or multiple imputation, which is not currently implemented for factor analysis in SPSS. You could do multiple imputation first and then run the factor analysis, but I prefer to use actually programs that allow me to implement full information maximum likelihood, such as Mplus, for example, or LAVAAN, which are also great programs for EFA. Anyway, so now we're stuck with SPSS here for the moment. So we're going to go with listwise deletion, which really is not ideal because you lose a lot of data potentially, and listwise deletion makes restrictive assumptions about the missing data mechanism. So keep that in mind, that if you have access to a better program, then you should use it. For example, a program for structural equation modeling such as Mplus or LAVAAN. Okay, let's go continue and let's click on OK. So we get the output for this factor analysis. You can see first we get our descriptive statistics, the means and standard deviations, and then we can also see the sample size, which is useful then and would otherwise not be provided if we hadn't asked for descriptive statistics. So this analysis is based on 384 cases, which should be plenty for 7 variables with I don't know, 1 or 2 factors, as we will see. So the sample size seems sufficiently large. From the correlation matrix, we can see that the variables are all substantially correlated. There's only one correlation here below 0.4, and it's still substantial, 0.384, and there are many correlations that are above 0.5. So This shows that this data set here is suitable for factor analysis. It would be problematic if the variables weren't correlated, then it wouldn't make sense to extract any factor. So you want to check that and check your correlation matrix, make sure that you have substantial correlations in the data so that factor analysis makes sense. We can also see that variables that pertain to the math scale tend to be somewhat more highly correlated with one another, and also those that pertain to the cognitive ability test, they also are more highly correlated than they are with other variables on average. However, those other correlations across the math and cognitive ability scale are still also pretty substantial, showing that math ability is positively related also to the ability that is tested with the cognitive abilities test. So it'll be kind of interesting to see how many factors we need here. Is one factor sufficient to reflect those correlations, or do we need more than one factor? Next are the communalities, where you can see that those are after extraction between 0.421 and 0.59. So they're relatively low, meaning that in this solution we have relatively little explained variance. However, that's not so meaningful for us right now anyway, because we're not even sure that this is a good solution that SPSS will offer us here. Next is a table with the total variance explained, where we get our eigenvalues in the column total, and then also we get percentages of explained variance, so we can take a look at how much variance each factor explains. The first factor here explains 56% of the variance, the next one then only another 10%, and then you can see subsequently the subsequent factors explain less and less variance, which is one reason why later on we will do factor rotation if we use more than one factor, so that we can balance out the variance more across different factors rather than having everything explained only by, or pretty much the majority explained by the first factor. Next is the scree plot. The scree plot is simply a plot of the eigenvalues that we already saw in the previous table, and you can see there's one very strong factor. The first factor has an eigenvalue near 4, and then the second factor already has an eigenvalue below 1. So this means that according to the Geiser criterion, SPSS would have extracted only one factor, and that's what it did. As you can see here, you can see that there's only one factor in the loading matrix that SPSS calls the factor matrix, because there's one factor with an eigenvalue above 1. So the scree plot pretty clearly shows that this is a strong, so say, G factor, and that reflects the fact that all of the variables in this correlation matrix here are highly correlated or substantially correlated, and that the correlations are of similar magnitude. So those reflect, all those variables reflect cognitive abilities, and so they are positively correlated. There's a strong underlying factor of cognitive abilities, and then therefore there's one that has a strong eigenvalue and the other ones are pretty flat. Now, that being said, that doesn't necessarily mean that a single factor solution is the best solution, even though you can see the factor loadings are pretty substantial on this single factor, ranging from 0.65 to 0.77. You can see one of the math subscales is actually the marker variable for this factor with the highest loading here. And so those are all pretty sizable loadings, but that doesn't mean that a single factor solution necessarily is acceptable. When we take a look at the goodness of fit test that is provided with maximum likelihood factor analysis, then we see that the test statistic here is significant. It's a chi-square test of model fit that tests the null hypothesis that the single factor model fits in the population. And you can see that that null hypothesis is rejected because the chi-square test is significant, indicating significant misfit of the single factor model. In other words, the model did not, or the data are unlikely to have been generated under the single factor model. There's something else. There must be more than one factor here to account for the correlation structure fully. So then we can go back to our option that we used previously and extract a second factor to see if that solution fits the data better. So I'm going back to factor analysis and extraction. And what I'm going to choose now is fixed number of factors 2, because we saw that a single factor model is rejected based on the chi-square test of model fit. It provides insufficient fit, so there must be more than one factor. And so then I'm going to click on continue, and we're going to evaluate the two-factor solution. However, in order to do that properly, we now also have to do factor rotation, because a factor solution with more than one factor that is not rotated typically is uninterpretable. So let's do that. Let's go to rotation and let's choose a method of rotation. So here the question now is, which rotational method should you choose? And so my recommendation is to use an oblique rotation method, meaning one that allows the factors to be correlated after rotation, as opposed to one that forces the factors to remain uncorrelated. The reason for that is that typically an oblique solution is more plausible and is more realistic because factors tend to be correlated. And especially in our case, where we have cognitive ability factors that are most definitely positively correlated, it would be unwise to assume, or unrealistic to assume, that the factors are uncorrelated. So a math ability factor, for example, would be correlated probably with a cognitive ability factor. And so therefore I'm going to choose a method that provides an oblique rotation such as ProMax. Another one would be Oblimin, which also allows factors to remain correlated. An orthogonal method would be Varimax, which then forces factors to remain uncorrelated, and I don't recommend that. What we can also look at is a loading plot, which will allow us to visualize how the variables load on the different factors. Next, we're going to go to continue, and then I'm going to click on OK again to see what the two-factor solution looks like. We get the same descriptive statistics table and the same correlation matrix that we've already seen before. And now we can see the communalities after extraction of two factors, and you can see that those are a little bit higher here than previously. So those are the variances, the proportions of variance that are explained by the two factors. And so you can see these range between 42.6% explained variance and 60.3% explained variance, which is relatively substantial. Next, we're going to go down and we're going to take a look at the chi-square test of model fit first to make sure that a two-factor model fits the data. And you can see now the chi-square value here is non-significant. The p-value is 0.08, which is greater than a common significance level of 0.05. So therefore, the two-factor model is not rejected, whereas the one-factor model was rejected. And so this shows us that we can potentially interpret this model and that that's potentially a valid model for these data here because it's not rejected according to this test. So then let's take a look at the factor matrix, and the factor matrix provides the unrotated loadings. And so here you can see that before factor rotation, factor 1 again loads all of the variables highly, whereas the second factor has an inconsistent pattern of small and partially negative loading. So you can see that before we do factor rotation, typically a solution with more than one factor is not interpretable, because that would mean the first factor again is a G factor of cognitive abilities, the second factor is nothing. Basically, it doesn't really have any variables that load highly on it, so the second factor would be uninterpretable. And that's why we do factor rotation, to balance out the variables across the two factors. And so let's see how that actually worked out. The pattern matrix provides us with the factor loadings after factor rotation. And here you can see that now we have a clear pattern of factor loadings where all the math subscales load highly on factor 1, and again they're sorted by size, so that makes it easy to see. They're actually in order, subscale 1, 2, 3, 4. The subscale 1 is the one that is the marker variable for this factor with a high loading of 0.78. And then the second factor you can see has high loadings of the cognitive ability variables, especially the figural subscale and the verbal subscale have loadings above 0.7 on this factor. The other loadings, the cross loadings, are all small. So for the math factor, the cross loadings are, for the math variables, the cross loadings on the second factor are below 0.2. For the cognitive ability variables, the cross loadings on the first factor are all also pretty small, except for the quantitative scale, which makes sense because that uses numerical mathematical material as well, and it has a relatively high cross loading of 0.246. So this means we can pretty clearly interpret those two factors. The first factor would be a math ability factor. The second factor would be interpreted as a cognitive ability factor. And you can see that the simple structure here is achieved very well by oblique rotation with Promax, where the factors remain correlated and the loadings have a pattern to where most variables have high loadings on only one factor and then a small loading on the second factor. The structure matrix is less interesting. Here in this case, it gives us the correlations of the variables with the factor, and you can see those are all high, so those don't provide such a clear picture. And so here the loading matrix is more interpretable, meaning the pattern matrix in terms of a simple structure. We also get a matrix of factor correlations since we did an oblique rotation with Promax. And you can see it was for good reason that we allowed the factors to be correlated, because the actually estimated factor correlation is quite substantial with a value of 0.774. Meaning those factors really are strongly related. If we had used an orthogonal rotation such as Varimax, then we would not have achieved such a good simple structure, because we would have incorrectly assumed that the factors are uncorrelated when they are in fact substantially positively correlated. Also, we can take a look at the factor plot in rotated space, which provides a graphical representation of the factor loadings, and you can see here that factor 1 is on the x-axis, factor 2 is on the y-axis. Factor 1 is the one that has all the math variables on it, in particular math 1 and math 2 with particularly high loadings, whereas the second factor, which is on the y-axis here, is the cognitive ability factor, which especially is marked by the figural and the verbal subscale of this test. The quantitative subscale is somewhat in between the two factors because it also uses mathematical numerical material, so it's a little bit more strongly related to the math factor, and so therefore has a cross-loading that is reflected by the fact that in this graph it is somewhat in between those two factors here. Now, one more thing is worth mentioning here, and that is that in SPSS we cannot really use ordinal variables when we do factor analysis, because SPSS doesn't have the proper techniques for using or to be applied for binary and ordinal variables, which would be a different type of correlation matrix that we should use. Specifically for ordinal data, we would use polychoric correlations and we would use different estimation methods. So if you have item level data, binary or ordinal data, you might want to choose a program that can handle those data better, such as Mplus or LAVAAN, which provide polychoric correlations and allow you to run factor analysis based on polychoric correlation matrices or tetrachoric correlations for binary variables. I hope you found this video useful to learn about how to run an EFA in SPSS. If you did, please subscribe to this channel and check out the description for additional resources, including workshops that I offer for QuantFish.